So we have learned an ARMO process. Autoregressive random process is a simplified version of that when L of Z numerator has no zeros, and your random process X of n can be created like that. So you can see that here X of n is equal to, this is the autoregression part, so it becomes B0 I of n minus autoregression part, which is this one. So here you see that this filter has B0, A1, and AN, which is n plus 1 parameters. So ARN random process has n plus 1 parameter, and you can calculate X of n if you have if you have I of n, and if you have these parameters. If you have these parameters, using this equation you can calculate X of n. Similarly, if you have X of n and your parameters, using this equation you can calculate I of n, just divided by B naught. So this relationship between IN and X of n is 1 to 1. So this is a representation. So, and this I of n is wide sensitive. So what is it is that X of n can produce I of n, and I of n can produce X of n using this autoregressive filter. So this, so here this is just moving average filter. So, and this is AR filter. So this is so if you get I of n to this L of Z, and here you put 1 over L of Z. Okay. So X of n therefore is represented by this signal, and if you have X of n you can calculate I of n, because you can calculate the autocorrelation function. And then so this is very interesting. For instance, in speech processing in linear prediction coding, the speech signal X of n is given to a linear predictor, and then in this linear predictor for a segment of your speech, these parameters A1 to AN and B naught are calculated. IN is also calculated. This vector is compressed and encoded and transmitted to the receiver. These INs is also some bits, not a lot, is transmitted at the receiver. This information is used to estimate another signal which sounds like X of n, because in speech this IN doesn't contain much perceptible information. So they produce another signal which is not equal to X of n, but it sounds like that. For image, this I of n contains more information. So autoregressive random processes, we have learned about it. Now suppose that we have an ARN process for speech, for instance. Usually they assume that the speech signals is ARN, and degree n usually for good quality speech is 12 for speech. For other applications you could use higher order, for instance in economy and so on. You can make the same assumption. So and then suppose that because you have X of n a random process, from these you can calculate the autocorrelation coefficient. So remember that X of n times x of n minus k, and then mean of that. So you can calculate that by averaging over time. So you could say that x of n minus k, and then put different values, put over some like n from n1 to n2, and then divide it by that. So on time domain, ensemble average could give you some estimate of that. Suppose that this one is given for, because how many parameters here we have? We have n plus 1 parameters. So n plus 1 parameters from autocorrelation function is necessary and sufficient. So the question is that how we can calculate this one. So this gives us a problem, which means that we have to try to use this equation in order to solve. So first of all, because I of n is a white noise, its samples are uncorrelated. So if I calculate the mean of x of n minus m and I of n when m is bigger than or equal to 0, we get this function. Okay, so if I multiply both sides of this equation by I of n conjugate, so we could quickly get. So if you so remember that this is delta Kronecker. Delta of n minus m is equal to 1 if n is equal to m and 0 otherwise. So if you multiply now this equation by x of n minus m conjugate for different values of n. So I first multiply by x of n and take expected value. Then I multiply by x of n minus 1 conjugate, and so on. So if I multiply this one by x of n conjugate, so this becomes x of n conjugate. If I take expected value, I get this one. These times this one expected value, get a1. Expected value of x of n minus 1, this one, so we'll give you this one, and so on. So you get this equation becomes this one. Then I multiply the same equation by x of n minus 1 and take expected value. Then I get another equation, which the first term gives you this one, the second term gives you this one, and the last term gives you this one. And if you multiply this one by x of n minus 1 conjugate, these two guys are uncorrelated because we had this one here. Okay, so we get 0. Now I multiply this one by x of n minus 2 conjugate, and then take expected value. I obtain another equation and so on. And then I continue and I multiply by x conjugate of n minus m, whatever number I want, or x minus n. And then I take expected value and I get this equation. So you can go up to n, but I need it up to here. So I get infinite number of equations, but I need to use only the first n plus 1. So I get also this equation. So what I have here is, from here to here, I have n plus 1 equations. These equations are linear in terms of, so obviously this guy, they can be calculated using data that I have. They could be learned using data. And therefore, I have this n plus 1 equation. However, these parameters a1, these parameter a1, an, b0, a1, an, they are unknown. So we'll have to solve them. So what I could do is to write the first equation in a matrix form. So I have the first equation is b0 to the power of 2 is equal to a1, a2 as a column vector, times a row vector of r x x of 0, r x x of 1, etc. So this equation is the first equation. The second equation, I could write it in another row of this matrix, r x x of minus 1, r x x of 0. So this guy comes here, this guy comes, and then instead of this side, instead of 0, I get 0 here. And so I could write, I could convert this n plus 1 equation, this system of n plus 1 equation, in a matrix form, which is called Yule-Walker equation. So I get n plus 1 linear equations with n plus 1 unknowns. Okay. Which, if we solve it, it will give us the solution. And these set of equations are linear in terms of these numbers. Remember that your unknown parameters here is b naught to the power 2, not b naught. So we can determine b naught to the power 2 and not b naught. So the sign bit is not calculated.